Okay, so I thought I'd record this video instead of writing it all out. So you found the first derivative, second derivative correctly, and then what when we're looking for maximums or minimums, we're going to find the critical values of the first derivative. So where is it equal to 0? This is a polynomial, so there's not going to be any undefined places where the derivative is undefined, so we don't have to worry about that. But so as you said, x equals 0 and x equals 2 are the zeros, or the critical values for the first derivative. And then I'll often, if I can, I'll factor it out a little bit to make it easier to do this next part of the calculation. So now, the next thing we have to do is test to see if these are if maximum values happen at these x values, or minimum values happen at x values, or if nothing happens at them. And chances are, usually, I won't say always, but if you find that a critical value of the first derivative doesn't have a sign change, it's going to be an inflection point. Not always, but usually. So what I did is, and I usually do this, so for the first derivative test, I'll make a number line. Let me get a pointer going. Let's see here. There. So I'll make a number line. I'll write in the critical values of the derivative, and then I'll test values either side of that. So -1, and pick easy values, because you don't really need to worry about the actual value. You just want to know if it's positive or negative. So I dropped in -1 into the function. Well, -9 times -1 is a positive number, and -1 minus 2 is a negative number. Positive times a negative is a negative, so the first derivative is negative left of 0. Then I picked 1, because that's in between 0 and 1. And if I drop in 1, let's see, that's negative times a negative is a positive. Okay, so anything in between 0 and 2, first derivative is positive. And then I chose 3. So that would be a -27 times a -5. That's -27. A -27 times a +1, because 3 minus 2 is 1. So it's negative. So the first derivative is negative. So what I'm seeing with this is the function's changing from a decreasing function to an increasing function at x equals 0. So that tells me this is going to be a minimum value in the graph. So then we go back in and substitute 0 in, we get -6. So there's a min of 0, and the minimum value is -6. And then there's going to be a maximum x equals 2. And so if we drop that in, there's going to be, I think you did this in your work, 4 times, well, let's see, -36. No, I don't want to look at the derivative. I want to look at the first function, don't I? So let's see, I guess I could do this one out. I can't, you probably did this on your paper. So what's f of 2? F of 2 equals -3 times 8 plus 9 times 4 minus 6. Let's see, that's 36 minus 6 is 30, and that's -24. I'm seeing 6, unless I'm making a mistake, which is entirely possible. So 6 is a maximum, and there's a minimum, and so this is a max. This is the mins happen at 0, -6. Now, that's the first derivative test and calculate it. You can do the second derivative test. I'll be honest with you, I don't always remember to do the second derivative test. But since we've already got it here, it's not all that hard. You see how, and I wrote this out earlier before I started this recording. Let me get a pointer going here. If I drop in 0, that critical value from the first derivative and the second derivative, I get a positive number. That tells me the function is concave up. So it looks like this. So that turning point is going to be a minimum. And then we just evaluate it. So you see how that confirms what the second derivative or the first derivative test gave us. Okay, I hope I'm still recording. Yeah. Okay, my internet dropped out. What else is new? And then, let's see. Of course, I lost all my Zoom work, so maybe I'll just do this with Paint. That way I don't lose it. And then if I noticed that you drop 2 into the second derivative and you get a negative number. So that tells me the function is concave down. Remember, if second derivative is negative, it's concave down. And that tells me that has to be a max. And of course, I lost my value, whatever 2, what was it? 2, I don't remember what the number was anymore. I lost it. Okay. So that's how you can use the second derivative test to do this. Now, the other thing that a couple of people have posted that they're having trouble with is inflection points. So just because the second derivative is equal to 0 doesn't mean there's an inflection point. You got to test and see if there's a concavity change either side of that inflection point. Because it is possible. I mean, what would it look like? It would look like, I mean, I could have this. Suppose this was my function. Okay, the second derivative is not going to be defined here at that cusp, right? And it's concave up either side of this. So that would be a situation where the second derivative would be 0 or undefined, but there's no concavity change. So what you got to do is look for concavity change. Here, let me clear this drawing out. Let me come back here. So let's see. So where does y double prime equal 0? Well, that's at negative 18x plus 18 equals 0. So I think you said that x equals 1. And that's right. Now we're going to check and see if there's actually a concavity change here. So 1 f double prime. And so if we drop 1, it's something to the left of 1 is 0. If we drop 0 in for that, that'll be positive 18, which is positive, right? If we drop in 2, that'll be negative 36 plus 18, which is negative. So yeah, this is an inflection point happens at x equals 1. Now you just go back up and find it. I think you did this negative 3 plus 9 minus 6. Oh, that's 0, isn't it? So at 1, 0, there's an inflection point. Okay, and that's how you use the derivatives to check.